Alright everybody, welcome to forward and inverse kinematics of a robotic arm. Today it's going to be quite a long problem, so it's going to be probably be two videos with the forward kinematics using DH notation and then inverse kinematics after we find that complete forward kinematics. Right here we're supposed to find the forward kinematics with respect to the position and the rotation of the vector of the arm. This will require that we use ZYZ. The reason we use ZYZ is because we have O and phi right here, which we have to use, and they both have to be with respect to Q. And the transposes and all that stuff, just make sure that you have them lined up with vectors. If you don't understand that notation, I recommend you become more familiar with vector notation, and that'll be a little easier for you. But we're supposed to use Denevit-Hartenberg VH notation, or a combination of translations and rotations. That's a little bit easier, so I'm just going to go ahead and use DH here because traditional forward kinematics is actually a bit easier and it's not very helpful if I do that in this video. So, using DH here on this problem, the robotic arm is already almost all defined. We just have to go and label everything and kind of define our axes for the DH notation. So starting out here, this will be J1, and then this joint will be J2, J3, and J4 right here. 1, 2, 3, 4. So since we have 4 joints, we know that our DH table is going to have 4 rows. That's a basic rule right off the bat. So now we need to go ahead and define our Z-axes. Z-axes are always in the direction of the axis of the joint or the direction of translation. So like in this case up here, this will be the Z. I'll go ahead and label these Z0. Then we've got Z1, Z2, Z3. And then we're going to make this one equal to Z4 because that's the approaching angle. And since we're able to continue on with that, we're going to go ahead and make this one X4 equal to Y4. Now you'll notice that these axes that I'm setting up are one number less than the joint number. That's required for DH notation. It becomes really important later on when you do a little more advanced inverse kinematics and Jacobians and that kind of thing. So you need to make sure that you have this notation correct. The Z0 is at joint 1, Z1 at joint 2, and so on and so forth. Up here, the reason I was able to define this as Z0 is because it is the same equal to the approaching direction. That is the direction of the claw. It goes in the direction of Z4. And then the common normal between it and this one will be X right here, and then Y is always the sliding angle right there. So the end effector axes just happen to end up aligning with our DH axes that we set up here. But anyway, continuing on with this, X is always in the direction of the common normal. So this is going back here. Since this is the first joint, actually, X and Y are automatically defined. So this is going to be X0, Y0. They're automatically defined like that. You just set up a normal axis, like down here at the base. Then moving up here, you see that you have the Z-axis going up like this, and then this Z-axis going along like this. You have a common normal between here. So since the intersection of the common normal and the Z0 axis is at P1, and then the intersection of the Z, excuse me, this is the Zi minus 1 axis and the common normal, and this is the Z1 axis and the common normal, because right across here, sorry, you probably can't see that, right across here is the common normal, because that is the place where you have a line that's 90 degrees with both the axes, if you drew it across there. So the common normal, this is going to be O1. And then since X is aligned with the common normal, which in this case is right here, X is going to go back here, so X1. And then setting up a normal axis, Y will come up this direction, so Y1 right there. Make sure you're drawing this out because I'm going to have to get rid of this picture later to do the rest of the work. Then in this case again, you're able to go through here, X2, and then Y2, oops, Y2. And then since we have the intersection of these two axes, the Z1 and the Z2 axes are intersecting right here, O is equal to P2 at this point right here. Then moving on up here, we've got X3, Y3, Y3. So that's pretty easy. There's a lot of stuff to have to put in here. This joint is going to rotate, and so on. So you can see how the rest of this goes. I'm going to go back and do Q's right now. Basically just drawing this out. If you're not familiar with this video, I'm going to skip a bunch of steps. So if you're not kind of aware of DH notation, you're going to get lost in this. So Q1, Q3, oh, I don't have to do that in this one. I apologize. The Q1s are already a supply force. But you can see this one has a rotation of Q1. I'm going to draw the arrow for it. This one has a rotation of Q2, arrow for that. And then this is Q3 going up and down like this. And then Q4, there's a rotation like that. And so on and that's it. So I think we've defined all our axes. And I hopefully you can kind of understand and were able to follow with me on what I was doing there. But now we have everything defined that we need to have defined in order to do our DH table. So, moving on from there. Oh, this is O3 equal to P3, by the way. And since these axes are actually aligned in this picture, you could actually put O3 and P3 anywhere along these axes. But it's just handier to put them there at the base of the axis system that we defined at that joint. Alright, so coming up here, starting on the new sheet. One thing I'm going to do before we get into the DH table, if we want to completely define the forward kinematics of this arm, we have to have the A matrices for this part of the arm and this part of the arm. The end effector and the base are not included in the DH solving. So we have to define those first. So I'm going to do the rotation about from B to 1 here, from 0 to joint 1. And that is going to equal 1, since there's no rotation from here to there. I can just say it's 0 rotation, which is going to be an identity matrix. So 1, 0, 1, 0, 0, 0, just like that. But then I also have an O of B to 1, the translation. And this is going to be equal to 0 in the x direction, because we're not moving back and forth this direction at all on this axis. But then it's going to be 1 in the y direction, moving in the positive y direction, and then 2 in the z direction. Or 2 right there. So there we go. And then if we put that into an A matrix from B to 0, or B to 1, B to 1, B to 0, it doesn't really matter. Oh, I apologize. It is B to 0. When you're doing these normal matrices, you go from this axis to that axis, not from like base to joint 1. I actually made the mistake I just warned you about. Always use the axis systems as a way of defining these matrices. So from the base axis system to the 0 axis system. This is going to be equal to 0, 0, 0, 1, 0, 1, 2, which is the O, and then 1, 0, 0, 0, 1, 0, 0, 0, 1. Sorry, I made that a little tighter than it should have been, but that's the matrix right there. Make sure you get those in there, spread them out however you want. And then I'm going to go ahead and do the A4 to E matrix, which is easier because you know how to do this already, so I'm just going to skip a step. I'm going to do 0, 0, 0, 1. This is the basic way of setting up an A matrix. You always have this bottom row set up like this. And then, since we're going from the the 4-axis system to the E-axis system, the end effector axis system, there's no rotation and there's no translation because they're the same one. So it's going to be a rotation of 0, 0, 0, 0, 0, 0, 0, and a translation of 0. So real easy to set up these two matrices right here. And these we will use in the future calculation for finding the complete forward kinematic matrix. So now, doing our DH table. Well, let's see how far I can get on this. So the DH table. We know that we're going to have 4 rows. We're going to have D, beta, A, and alpha. And 4 rows, 3, 4. And we're going to go from the 0 axis to the 1 axis, then 1 to 2, and then 2 to 3, and then 3 to 4. And then we'll have a complete VH layout. So, going from, let's see how I can do this. Yeah, that'll work. So, going from 0 to 1 up here, you can see that D, we're going to have a translation of 2. So let me state the rule out loud here to make sure it is. So, D is the coordinate of P1, Pi along the Z I minus 1 axis. So in defining D, you're going from the Z minus 1 to the location of P along the Z axis. So in this case, it's just 2. Pretty easy. And then for theta, theta is the angle from xi minus 1 to xi from about zi minus 1. So from this x to this x, about this axis, the z axis. So this is going to equal, let me make sure I got this right. I messed that up somehow. It's going to equal, theta is the angle from x of I minus 1, x of 0, in this case, to x of I, which is x of I minus 1. Let me double check something here. I think I made an error. Oh, no I didn't. I was just being confused. I was thinking in degrees and not radians. But, so you have a 180 degree split turn around this axis from x0 to x1. So we're going to have a rotation of pi. Let's split those up a little bit. Pi originally, but since Q1, this is a revolute joint, Q1 is also going to add to that. So you're going to have 180 plus whatever Q1 adds. So plus Q1. And then alpha is the distance either of the common normal, you could say it's the distance of the common normal, or as the distance from Pi to P0, which is basically the distance of the common normal. So in this case, it's this distance along here, which is 1 meter. And then alpha is defined as the angle from Zi minus 1, so Z0, to Zi, which is Z1, about the Xi axis. So from this Z to this Z, about this axis. And in this case, it's 90. So, and the way you can define that is using the right-hand rule. You know it's positive 90. Put your thumb in the direction of the x1 axis. Curl from Z of 0 down to Z of 1. And you'll know that it's positive if you don't have to do anything funky, if your thumb still lines up with the x minus 1. So right-hand rule. So it's pi over 2, which is 90 degrees. Okay, now we'll be able to blaze through these a little faster now. So distance along the z-axis from 1 to 2 is going to equal 2 meters. Theta is going to equal, I broke my leg. Theta of x of 1 to x of 2, about z of 1. So x of 1 to x of 2, it's 180 again, and we know it's positive, so it's going to be pi. Let me get my lid working here. Pi plus, again, it's a revolute joint, so Q2. And then alpha is equal to 0 because O2 and P2 are in the same spot. And then alpha is going to equal Z1 to Z2 about X2. So right-hand rule, Z1 to Z2, positive pi over 2, 90 degrees. And then up here, we have a translational joint. So the distance from to P2 from the axis, or P3 from the axis, is going to equal whatever Q3 is. So we've got Q3. And then theta, since the axes all line up, there's not going to be anything, so that's going to be 0. And then alpha, Again, there's no distance between 0, 3 and 0, P3, so that's going to be 0. And then alpha, also, again, no rotation about x0 because the axes are exactly the same, or x2 or x3, that's going to be 0. And then going from the 3-axis to the 4-axis, we're going to have a distance of 1 meter, because this is where P0 is, I should say, 0 to 4 and equal to P to 4 right here, up here at the top. And then theta, well, we have no rotation between these two axis systems along the Z3 axis. So there's going to be a 0 rotation, but since it's a revolute joint, you still have an angle that's created by that. So plus Q4. And then A is going to equal 0 because O and P are on the same spot, and then alpha is equal to 0 because there's no rotation. And now, looking at your DH table, we've fulfilled all the requirements. We've filled up all 4 rows. But then you'll notice that in each one of these rows, you have the variable of the joint. So Q1, Q2, Q3, Q4. And you can tell that you have completed the DH table correctly because anywhere there's a joint, you have to do a row. You have to include that joint variable in the row that that joint is being defined in. If we didn't have a Q1 in the first row, then we know we made a mistake because Q1 should be defined somewhere. So if you're ever working with a DH table and you end up with, and you're defining all the joints and you end up with a row that either has an out of place Q variable, like if I had Q4 in here or something like that, then you know you made a mistake, or if you're missing the variable completely, you know you probably made a mistake. So that's the DH table. Now, I'm not going to write out the equation right here because it's, no, I'll write out the equation. You use the DH table now to find your 4 kinematics by using the equation of ADH, which I'm going to call A of I minus 1 to I, is equal to, this is a gigantic equation, C times theta I minus S theta cosine theta, oh, no, cosine alpha. Cosine alpha I, sine of theta I, sine of alpha I, I, cosine theta I. Actually, I'm not going to finish this. I'm going to give you the general formula, and you can look up the DH formula on your own. That'll take about 2 seconds to Google or look up in your textbook. And then fill out the rest of this, and you have the DH equation that you need in order to turn this DH table into an actual forward kinematic matrix, or an A matrix. So just use Mathematica or MATLAB in order to do that, and then you'll be just fine. Because that's the only way you can do it, actually. To do this by hand would be very difficult. Alrighty then, so moving on from there, you have the DH table defined. What I'll write out, instead of writing out that whole matrix, is the result that you should get if you do that in MATLAB or Mathematica. A, B to E. Now you'll notice that I also included, I'm going from B to E, so I'm including the 2 matrices that I defined earlier also. So you get the A 0 to 4 matrix from these, but then you have to combine that with the A, B to 0 and the A4 to E, and you just do that by multiplying the matrices together. And if you do that, you will end up with the answer of cosine of 1, cosine of 2, cosine of 4 minus sine of 1, sine of 4, then minus cosine of 4, sine of 1, minus cosine of 1, cosine 2, sine of 4, cosine of 1, sine of 2, and there's going to be something else added on here that I'll put up down in the bottom here after I finish all the rows. Cosine of 2, cosine of 4, sine of 1, plus cosine of 1, sine of 4, then cosine of 1, cosine of 4, minus cosine of 2, sine of 1, sine of 4, sine of 1, sine of 2, dot, 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 then minus cosine of 4, sine of 2, sine of 2, sine of 4, cosine of 2, and then the normal A matrix row, 0, 0, 0, And now, going down here to the last part of it, we're going to have minus 2 sine of 1 plus cosine 1 of sine of 2 times 1 plus q3 minus 1. And we're going to have 1 plus 2 cosine of 1 plus sine 1 of sine squared of 1 plus q3 minus 1. And 4 plus cosine of 2 of 1 plus q3. This is just a label, by the way. It's not an exponent. It's not cubed. It's q of 3 over 1. Alright, so right here you have the complete rotational matrix. This part up here is the rotational matrix. R is equal to R from B to E. And this right here is equal to O from B to E. So you have a completely defined system now. And the only thing you have to do to get the forward kinematics is use the ZYZ relative calculation in order to get your forward kinematic vector. So, using that, you have phi is equal to A tan 2 of sine 1 sine 2 cosine 1 sine of 2. And the reason I got those is from here and here, right there, in this part of the matrix. You should know these formulas by now. And then theta is equal to A tan 2 of the square root sine 1 squared sine 2 squared plus cosine 1 squared sine of 2 squared by cosine of 2. And then this is equal to A tan 2 of sine 2 sine of 4 by sine of 2 cosine of 4. Alright, and then solving these out, you can actually do most of this mentally, because A tan 2, it's this over this, so you can cancel sine 2 and sine 1, which is going to, and then doing the tangent, the arctangent of the tangent, which is sine over cosine, this is just going to equal q1. And then this is going to equal, this one you might actually have to do the math. Oh, no, you don't. You've got the cosine 1 and cosine 2 right there, which cancel, because sine squared plus cosine squared is equal to 1. And then you've got the sine squared plus sine squared. Take the square root of that, cosine squared, square root of sine squared. This is all going to turn into sine squared, basically. Sine of 2 squared. That's what that's all going to turn to, and I can't show that to you right here, because you should know how to do that also, because that's old algebra and trig identities. But then you got sine 2 squared over cosine, or sine 2 over cosine 2, which is going to give you q2, and then this one again, sine 2, so I was going to cancel out, and you got sine over cosine, inverse of that, which is going to give you q4. So, now you have your x, y, this is equal to your x, y, z, because this is your position vector, basically right here. X, y, z right here, and then you've got your rotational vector defined right here, which is q1, q2, q3. So, your forward kinematics are equal to forward kinematics of q is equal to minus 2 sine 1 plus cosine 1 of sine squared of 1 plus q3 minus 1. And then 1 plus 2 cosine 1 plus sine 1 of sine 2 sine of 2, 1 plus q of 3 minus 1. Then 4 plus c of 2, 1 plus q3, all over q1, q2, q4. Send that out a little bit more. Now this part is your x, y, z, theta, or phi, theta, and psi. And that is your complete forward kinematic vector. And you have the forward kinematics of this arm. And that's all there is to it, really. It's a little labor intensive, but it actually simplifies pretty quickly, and once you're used to it, it's fairly easy.